Imagine trying to focus a camera lens on a distant mountain range to capture its grand scale.
Yeah.
But simultaneously, you're trying to focus that exact same lens on a microscopic bug sitting right on the glass.
Right. The physics of the lens simply will not allow it. You just end up with a blurry mountain and a blurry bug.
Exactly.
Eta.
And honestly, that is precisely what is happening inside the neural pathways of modern AI right now. So today on AI Paperslop, we are giving you the core insight right at the top. We are summarizing a paper called Uni-Edit. Intelligent editing is a general task for unified model tuning.
Yeah, and that is by Dain Zheng and colleagues from CUHK, Meituan, TJU, and USTC.
So unified multimodal models, the models that try to both understand images and generate them, they are currently stuck in this fundamental tug of war.
And the standard industry fix is just to juggle massive, messy, multitask data sets. They basically hope the model doesn't forget how to classify a dog while it learns how to draw one.
Right, but these authors prove you can throw out that entire delicate balancing act. They demonstrate that a single reasoning-intensive task can simultaneously upgrade a model's understanding, generation, and editing skills all at once.
Yeah, and specifically, that task is complex image editing using nested logic. They achieve this by turning visual question-answering datasets into multi-step editing prompts.
I mean, it is like asking the model to solve a geometry problem and then render the proof onto a digital chalkboard. And they combine that dataset with this brilliant architectural hack.
Oh, yeah, they completely drop the variational autoencoder features during training. It forces the generation head to rely 100% on the understanding branch.
So you just get a comprehensively smarter model. Let us get into the structural mechanics behind that tug of war we mentioned, because it is basically the most frustrating bottleneck in modern machine learning.
Well, yeah, UMMs are attempting to be the ultimate generalists. We want them to ingest and understand the visual world, but also, generate and create within it.
But those two tasks demand entirely conflicting things from the deeper layers of a neural network, especially in how backpropagation updates the model's weights.
Right. For any ML engineer watching this AI Paperslop breakdown, they know this conflict intimately. It is essentially a gradient tug of war happening inside the loss landscape.
Exactly. When we look at image understanding, the network requires high-level semantic abstraction.
I mean, the model needs to look at a chaotic, highly detailed scene and compress that information into distinct concepts. It needs to strip away the noise.
Right, like the specific lighting gradients or the exact pixel arrangement, just to recognize that a furry shape with floppy ears is a dog.
So the gradients from the understanding loss function are actively pulling the network's weights toward that conceptual abstraction. But generation, conversely, demands hyperspecific structural details.
Yeah, a generator needs to care deeply about every single pixel, the microtextures, the exact interplay of light and shadow.
So in those deeper layers of the network, the gradients from the generation loss are pulling the weights in the exact opposite direction toward granular specificity.
It is like asking a single master architect to conceptualize the abstract philosophical purpose of a massive skyscraper.
Right, the grand semantic vision.
Exactly. But then in the exact same breath, demanding they manually lay every single brick, wire, and pipe in the entire building.
If the architect focuses too much on the grand vision, the plumbing fails.
And if they focus too much on laying the bricks perfectly, the building loses its structural purpose. And honestly, current industry solutions really just reflect a struggle to manage that failure.
We see teams relying on architecture decoupling, like with Janus Pro. They physically separate the pathways for generation and understanding.
Or, in models like Bagel and EMU 3.5, they perform these incredibly delicate data mixing balancing acts. They monitor convergence speeds and dynamically adjust data ratios on the fly.
But those methods are essentially band-aids. They are just managing the degradation of the loss landscape to prevent either side from collapsing.
Right. They are not achieving true mutual reinforcement. Which raises an obvious question for you. If the architecture is inherently conflicted, why try to fix this in post-training data? Why not just build a better architecture from scratch?
Well, retraining these massive UMMs from scratch requires a staggering amount of compute. It is just prohibitively expensive for most of the open source community.
So finding a post-training task that naturally aligns both skills is basically the holy grail.
Exactly. And that leads us directly to the author's central hypothesis. They identified image editing as the theoretically perfect general task.
And logically, that makes total sense. To edit an image, you inherently need deep visual understanding. The model has to parse what objects are there and their spatial relationship.
But it also requires high fidelity generation. The model has to actually execute the change seamlessly and realistically.
because a deficiency in either semantic reasoning or spatial generation leads to total editing failure. So to test this, the researchers took Bagel, a state-of-the-art open-source unified model.
And they fine-tuned it on existing standard open-source editing datasets, specifically the Uni-Edit dataset.
But here is where we hit the dumb data trap. The results of that experiment were a complete paradox.
Yeah, when they fine-tuned Bagel on standard editing data, the model's understanding capabilities didn't improve, they actually declined.
Wait, if editing inherently requires understanding the image, why would training on editing make the model dumber at understanding?
Well, the root cause lies in the semantic shallowness of the data. Existing editing instructions in datasets like Uni-Edit are simply too simplistic.
You mean like prompts that just say, make the car red?
Exactly, or remove the tree. These instructions severely underutilize the model's high-level cognitive capacity.
So when the model processes, make the car red, the generation branch gets a massive workout blending red pixels.
Right, but the understanding branch, particularly the deeper layers of the vision transformer, the VIT, it is essentially starved of complex semantic challenges.
Because the task is so simple, backpropagation doesn't send meaningful updates to those deep reasoning layers.
And over the course of training, because those weights aren't being actively challenged, the understanding branch just atrophies.
Going back to that architect analogy, if you only ever ask them to repaint the mailbox, they are eventually going to forget how to design load-bearing walls.
Exactly. The data simply did not demand enough cognitive load.
So we have to make the data smarter. And this leads to the core of the paper, forging the Uni-Edit pipeline. They built a completely new data set from scratch, Uni-Edit 148K, and a tailored 40K subset.
And the pipeline they built is honestly brilliant because they didn't start with editing data at all. They started with visual question answering data.
Right, they leveraged the LLM Vision 1.5 dataset, which is already rich in complex reasoning tasks.
And they used GPT-4o to classify those VQA questions into highly specific cognitive categories, things like shape, color, count, location, OCR, caption, and math.
The critical innovation was the prompt engineering. They transformed those static questions into dynamic, reasoning-intensive editing instructions.
The nested logic they embedded into the prompts is the secret sauce here.
Let us walk through the math example, because the token-by-token processing required is mind-blowing. In a standard VQA dataset, you might have an image of a right triangle.
And the descriptive question is just, giving side AB is 8 and side BC is 14, what is the length of side AC?
But for Uni-Edit, they transform that into an active editing instruction. It reads, solve this problem with detailed process and final answer, then write it onto a parchment using a serif font.
The cognitive chain of events you are forcing the model to execute is incredibly dense. It cannot simply recognize a shape. It has to act as an agent.
Right. It must parse the text, align it with the VIT visual tokens representing the triangle, extract the numbers, and execute the math.
It has to hold that logical output in its internal state, and then, only then, condition the generation branch to render that proof into specific pixels for a parchment texture in a serif font.
It perfectly bridges deep semantic reasoning with high-fidelity pixel generation. And they applied this nested logic to attribute questions, too.
Yeah, they would provide a reference answer and force a logic gate before generating a single pixel. Like, identify the shape of the large purple object. If it is a sphere, change it into a cube. If not, do nothing.
By forcing the model to solve a conditional logic gate first, the understanding branch remains highly active and penalized for errors the whole time.
The model must explicitly solve the underlying semantic problem before it is allowed to execute the edit.
But having these dense prompts is one thing. They still needed the actual ground truth edited photos to train the model against.
So to generate this massive data set, they used Banana Pro or Nano Pro as their editing backbone.
But because the instructions were so nested, they had to feed NanoPro the ground truth answers from the original VQA dataset as contextual hints, just to make sure it generated logically correct target images.
And even with those hints as a crutch, NanoPro still had about a 10% error rate. Generating complex edits is remarkably difficult.
So to ensure the highest fidelity for the final dataset, they integrated GPT-4o back into the pipeline as an automated evaluator.
Right. They fed it the original image, the generated image, the instruction, and the ground truth answer. GPT-4o acted as a rigorous filter,
Throwing out any generations that failed on instruction following, aesthetics, or logical coherence. You absolutely have to do that to prevent the model from learning compound error loops.
Okay, so now we have the pristine Uni-Edit dataset. Let us transition into the training scheme because they deploy a technical hack here that completely alters the gradient flow.
They used Bagel as their base model, which is crucial since it is already a top-tier open-source architecture.
Yeah.
If it works on Bagel, it proves the paradigm works on state-of-the-art systems.
Yeah, so they set up stage 1 of training, and they fine-tuned Bagel using only the generation loss.
Wait, hold on. I'm going to push back on this right away. Because any ML engineer listening is immediately going to flag a massive problem.
Right.
If the loss function is only calculating error based on how well the model generates the final pixels, how on earth is the understanding branch actually learning anything new? Doesn't the gradient just update the generation head?
That is the exact paradox they had to solve. And their solution is a masterclass in manipulating network architecture.
All right, lay it out.
In the standard Bagel architecture, the generation head receives inputs from 2 pipelines. The VAE features, which are the semantic visual tokens from the understanding branch, and the VAE features, or variational autoencoder features.
And the VAE features are the highly compressed, latent representations dedicated to mapping pixel space, right?
Exactly. So what they did was intervene in that pathway and set the dropout rate for the VAE features to 1.
Oh, wow. Meaning 100% dropout. They completely turned off the VAE feature pipeline during the entire training phase.
Yes. By starving the generation head of its dedicated pixel pipeline, they triggered a massive shift in how the loss landscape is navigated.
The generation head was forced to rely entirely on the VAT features flowing from the understanding branch.
So when the model calculates that generation loss, the backpropagation algorithm cannot route the error through the VAE. The gradient has to backpropagate entirely through the VAT understanding encoder.
That is genuinely brilliant. To minimize that generation loss, the understanding encoder is forced to upskill massively. It has to extract visual features robust enough for abstract comprehension and pixel-perfect rendering.
They basically tied one hand behind the generation branch's back. Because the dedicated generation pipeline was shut off, the understanding branch had to shoulder the entire cognitive load.
Which fundamentally rewired it to become stronger at everything. It forces the VIT to master fine-grained detail without losing its semantic grounding.
Now, there is a stage 2 to this training scheme, and it comes with a fascinating caveat. Because they only used generation loss in stage 1, the language modeling head wasn't directly optimized.
The part responsible for outputting explicit PEX tokens. So they ran a standard alignment phase using 80K Elabi1 samples just to align the language head with the newly sharpened VIT branch.
But the ablation studies revealed something counterintuitive. While stage 2 improved text-based understanding tasks, it actually degraded the generation and editing performance slightly.
Right, which highlights a profound gap in our current architectures. It proves there is tangible friction between a model recognizing a semantic concept in its internal latent space and explicitly projecting that into rigid text tokens.
Forcing the network to align its internal representations with human language actually pulled those representations slightly away from the optimal mathematical state for visual generation.
So let us talk about how this translates to real-world performance. The scorecard for this method is staggering. Just by using this single intelligent editing task and the dropout hack, Bagel saw massive simultaneous gains.
On the MMMU benchmark, which tests multidiscipline reasoning, it jumped to 53.6. On Math Vista, evaluating deep mathematical logic, it hit 73.8.
And on the RISE benchmark, which specifically isolates complex reasoning-based editing, the model leaped from a baseline of 11.9 all the way to 17.2.
To truly grasp why these improvements are so sweeping, we have to look closely at their data diet ablation studies. They broke down the dataset by cognitive categories to see what drove which gains.
And this breakdown perfectly explains why the Uni-Edit data failed so spectacularly earlier. When they trained solely on attribute data, basic shape, color, and count identifications.
It heavily boosted the pure generation scores, but severely degraded understanding, because identifying basic colors is too visually intuitive.
It doesn't require deep world knowledge. The deeper semantic reasoning layers aren't challenged, so they get lazy and performance drops.
Conversely, training on the knowledge data subset forces the model to recognize complex, multidisciplinary entities. That uniformly boosted performance across the board, driving the massive MMMU gains.
Furthermore, the location data subset heavily amplified spatial reasoning capabilities. That led to massive gains on generation benchmarks like Gen of all and WISE.
But out of all the tests they ran, the joint training ablation is the one that really defines the the paper.
Yeah, they ran a control test where they froze the understanding branch entirely during training. The logic was, maybe if the understanding branch was stable, the generation branch could focus its compute and learn faster.
And the result completely dismantled that logic. When the understanding branch was frozen, generation performance barely improved at all.
This proves something foundational. It proves that understanding isn't just a separate parallel skill sitting on an adjacent server rack. Understanding structurally underpins the ability to generate.
You cannot build a great generator without a razor-sharp understander serving as its foundation. They are fundamentally entangled.
It provides empirical validation for the entire unified model hypothesis. Visual comprehension and visual creation are not competing tasks. When forced through a reasoning-intensive bottleneck, they are symbiotic.
I do want to mention one very specific resolution quirk they documented just for the engineers. Keeping the original bagel resolution of 224 by 518 was absolutely vital.
Right. When they tried increasing the VIT input resolution to match high-end understanding tasks, it completely broke the performance. It seems like changing the resolution disrupts that delicate mathematical balance from the VAE Dropout Hack.
It is a stark reminder that these models are incredibly complex, non-linear systems. You alter one foundational parameter, and the entire loss landscape shifts unpredictably.
So bring this all together. The massive win here is the sheer elegance of the solution. We are talking about one task, intelligent editing, one data set, Uni-Edit, one training stage.
No more incredibly complex, fragile, multitask balancing tricks weighing down your compute. Intelligent editing is the general task required to push unified multimodal models forward.
It forces the architecture to synthesize abstract logic and granular pixels perfectly. And we want to leave you with a concept to chew on based on that synthesis. Throughout this paper, we saw that forcing a model to show its work, like rendering math onto a chalkboard, made its internal latent representation smarter at pure abstract reasoning.
So if generating a visual representation of logic actually improves the logic itself.
Exactly. Could the future of artificial general intelligence training involve models continuously generating internal, unseen visual sketches to solve complex logic problems? Are we heading toward a future where we finally bridge the gap between pixel space and pure reasoning by teaching AI to close its eyes and visualize the math?